Bismillah ar-Rahman ar-Rahim. Still we are in chapter number 1, and today we will continue with part 2 of chapter number 1, which is also about poor quality terms. When we say fundamental component, that means it is the component of order 1 of Fourier series of a periodic quantity. Of course, in Oman, the frequency is 50. So when we say the fundamental component, that means we are talking about the 50 Hertz component, or it is order number 1. Of course, if it is 100 Hertz, second order, 150, third order. Harmonic component, it is a component of order greater than 1. Okay, so starting from 2 upward. Harmonic content, the quantity obtained by subtracting the fundamental component from alternating quantities. Okay, so if we have such kind of, let us say, waveform with harmonic, then if we take out the fundamental of this one, then the remaining component in the waveform will be only harmonic. Harmonic number, it is the integral number given by the ratio of the frequency of a harmonic to fundamental frequency. So it is number 2, 3, 4, and so on. Tripling harmonics, a term frequently used to refer to the odd multiple. It is odd multiple of the third harmonic, which deserve special attention because of their natural tendency to be zero sequence. So tripling harmonic, that means we are talking about 3, harmonic 3, 3 times 2, 6, 3 times 3, 9, 3 times 4, and so on. So those we call it tripling harmonic. Those harmonic will be in phase with each other. That means if you have phase A, B, and C, so the harmonic that come, the third harmonic from phase A and third harmonic from phase B, third harmonic from phase C, they will be in phase. So there will be no phase shift between the third harmonic in different phases. Same thing apply for the 6th, 9th, 12th, and so on. Harmonic distortion, it is a periodic distortion of the sine wave. The level of distortion is assessed in terms of total harmonic distortion, as we have discussed it in the previous I can say chapter, in part 1 of this chapter. Okay, so total harmonic distortion, as we said, it is in the ratio of the root mean square of the harmonic content to the root mean square value of the fundamental component, expressed as a percent. As we have discussed it previously, we said that total harmonic distortion will be given by, you will take the sum of the square root of the harmonics starting from the second. Okay, and so it will be IH square. So we'll take the summation of the root mean square value for all harmonics. Okay, and you will divide that one by the fundamental component. Okay, you will divide that one by the fundamental component, which we call I1. So all of these are under square root. Okay, all those will be under the square root according to the definition. Total demand distortion, also we have already derived a formula for that previously, or I explained this formula. So to the ratio of the root mean square of the harmonic content to the root mean square value of the rated or maximum demand fundamental current. So over here in the total harmonic distortion, we are dividing by the fundamental current. Over here we are dividing by the maximum demand current. Of course, we're going to solve problems later on related to the total harmonic distortion and total demand distortion, inshallah. Okay, interharmonic component, a frequency component of a periodic quantity that is not integer multiple of the frequency at which the supply system is designed to operate. So we said that harmonics, it is the integer multiple of the fundamental. So we have second, third, fourth, fifth, and so on. But for the interharmonic, it is not the integer multiple. So it will be a fraction of that. So we can have 1.5, 1.6, and so on, times the fundamental 1.5 times the fundamental, or 1.6, 2.2, 2.5, and so on. So that's why we call it interharmonic. Frequency deviation, an increase or decrease in the power frequency. The duration of the frequency can be from several cycles to several hours. So again, we have standard. There is Oman standard. There is also IEC standard related to the frequency during the normal operation, or during, I can say that, abnormal condition. So they give a certain range for the frequency deviation. During the normal condition, so the frequency can go up to 50.05, or it can go to by 49.95, or something which are close to those numbers. Frequency response in power quality using generally refers to the variation of the impedance of the system as a function of the frequency. So when we say that calculate the frequency response, we mean we're gonna find the relationship between the system impedance as a function of the frequency. And again, we're gonna solve some problems, and we're gonna do the simulation by using MATLAB to find the frequency response of some circuit. Waveform distortion, a steady-state deviation from an ideal sine wave of a power frequency, characterized by spectral content of the deviation. There are, so for example, when we say waveform distortion, such as this one, so we're supposed to have pure sinusoidal, but because we have those over here, so this is not pure sinusoidal. Same thing, we're supposed to have for the current also a sinusoidal waveform, but we have those two pulses over there and over there. So as a result, over here we have a waveform, we call it waveform distortion. And also, as we have mentioned it already in part 1, there are 5 types of waveform distortion. So it can be due to the DC offset, it can be due to the harmonic, interharmonic, notching, and noise. Harmonic filter. So it is a device for filtering one or more harmonics. So now we are saying that because we are using power electronics, we are using non-linear load in power system, we're going to have some harmonics. How to reduce this harmonic? We can reduce this harmonic by having filters. So we can have what we call it passive filter, which mainly consists of LCR, or active filter, which mainly consists of power electronic device. Okay, so inshallah we're gonna talk about both later on. We're gonna also able to design a passive filter for a number of harmonic. So most of those filters are passive combination of inductance, capacitance, and resistance. And of course we have, so those are the most common type of filter. We call it passive, but also we have what we call it new technology of filter, which is called active filter. And again, the purpose of both the passive and the active is to eliminate the harmonic. Okay, again, this is the passive filter. So we said that it is a combination of RLC designed to eliminate one or more harmonic. The most common variety is simply an inductor in series with a shunt capacitor like this one, which short circuit the major distorting harmonic component from the system. So this is the most commonly used type. What will be the function of those? So this is over here we have polyphonic device, they will create harmonic. So the function of this filter is to take out the harmonics. It will not allow it to go in the system. So it will prevent the harmonic from going back to the power system. Okay, so this is again, this is the active filter. So it is the active filter utilize polyphonic device, and again the purpose is to eliminate the harmonic. Over here we have non-linear load that will draw non-sinusoidal current. As a result, the current taken from the source will be non-sinusoidal. Then the function of this filter is to provide a current to the system such that the current taken from the main source will stay sinusoidal, because as you know that according to Kirchhoff current law at this node, the summation of the current entering should be equal to the current leaving. So the current enter was supposed to have pure sinusoidal. Over here we have harmonic. Then over here also we have to provide a harmonic source such that this current will stay sinusoidal. Anyhow, we're going to talk about inshallah that one later on. Okay, we have what we call it voltage change and voltage fluctuation. So in the voltage change, it is a variation of the root mean square value of the voltage between two consecutive levels sustained for definite but unspecified duration, such as over here. So you can see that we have a voltage change. So the voltage is not, I can say, it does not stay to be identical. I mean, the different phases we're supposed to have, they have exactly the same magnitude. The phase difference between the different phases should be 120, but over here we don't have that. So then we call it, what we call it over here, we have a voltage change. Whereas voltage fluctuation, so it is clear we have fluctuation. So sometimes we have small voltage, peak voltage, and so on. And same thing is applied to the negative side. So it is a series of voltage change or a cyclic variation of the voltage envelope. Okay, so if we draw the voltage envelope, it will look something like that, right? So we have a kind of a series change. Okay, over here we have low, low, high, high, and so on. When we say non-linear load, it is a load in which the relationship between the voltage and current will not be linear. Okay, so they will not be linear. For example, if we have a linear resistance, the relation between the voltage and the current will be linear. But when we say non-linear load, so the relation between the voltage and the current will not be linear, such as if we have a transformer. So in this transformer, since the transformer is working at saturation, then the relation between the voltage and the current will not be linear. We have also some resistance, which is also not linear as well. Okay, we have talked also about the under voltage and over voltage. So under voltage used to describe a specific type of long duration variation referred to a measured voltage having a value at least 10% below the nominal voltage. For example, over here, this is our rated voltage over here. So any voltage below that, we call it under voltage condition. And of course, we call it under voltage if the time is more than 1 minute. If the time is less than a minute, then we call it voltage sag. Okay. Same thing will be applied for the over voltage. So over here we have more voltage compared with the rated value, and it is also more than a minute. So that's why we call it over voltage. If the time is less than a minute, we call it voltage swell, right? Well, transient, so it is a phenomena that varies between two consecutive steady state during a time interval that is short compared to the time scale of interest. A transient can be unidirectional impulse, or damp oscillatory wave. Okay, or this one, what we call it, notching. Right, so all this one we call it transient. Okay. And we said already, this oscillatory due to the capacitor energization. This notching, it is due to the short circuit when the electronic devices are working. And this one, it can be to also, let us say, to some switching. Okay, so we have a transient such as those, and we have oscillatory transient such as this one. So oscillator transient, they define it as a sudden non-power frequency change in the steady state condition of the voltage of the current that include both positive and negative quadratic value. See this one. So we have transient and we have oscillatory transient. Impulse. Impulse, it is a pulse that approximates a unit pulse. When used in relation to monitoring power quality, it is preferable to use the term impulsive. And instead of impulse, we call it what we call it, impulsive transient. And this is the kind of the impulsive transient, like the lightning strike, right? So the current will shoot to very high level in roughly microsecond, then it will decay to the normal level also in a number of microsecond as well. So impulsive, it is a sudden change in the steady state condition of the voltage or current that is unidirectional in polarity. Okay. So this is what we mean by the impulsive. So this is impulsive transient. Power factor displacement. So it is the power factor of the fundamental frequency component of voltage and current. So when we say that, calculate the displacement factor, so that means we need to find the angle between the fundamental component of the voltage and the current. So the fundamental component. So that's why I put 1. So the angle between those two, we call it displacement factor. Displacement factor or displacement power factor. And what is a true power factor? Because we have displacement power factor and we have a true power factor. It is the ratio of the active power to the apparent power, right? So we know that S is equal to P cosine, right? So cosine will be equal to S over P. So to the ratio of the sorry, to the other way around. Sorry, so it is P is equal to S cosine. So what is cosine? It is P over S. So it is the ratio of the active power to the apparent power. And again, we're gonna take some tutorial problem later on, and we're gonna show you how to calculate the displacement power factor and the true power factor. Of course, over here we are talking about harmonics, okay? We're talking about a waveform that include harmonics. If we are looking at the waveform that is without the harmonic, of course, those will be the same. The power factor and the displacement factor will be identical. Okay, crest factor. What is the crest factor? It is the value reported by many power quality monitoring instrument presenting the crest factor. Crest factor is defined as the ratio of the peak value to the root mean square value. Peak over root mean square. For example, if we have sinusoidal waveform like that, so this is the peak, this is the root mean square, so the relationship between the peak and the root mean square will be 1.4. Then we call the crest factor of the sinusoidal waveform will be 1.4. Distortion is any deviation from the sinusoidal waveform, right? As we said, we're supposed to have pure sinusoidal, but we're gonna have such kind of waveform. Then over here we have a distortion. Current distortion, same thing. Voltage distortion in the AC voltage. Okay, of course this one shows also what we call it voltage imbalance. Okay, so the voltage of different phases are not identical, so we call it voltage imbalance, and this is the measured result in distribution system in Oman. Okay, we have another term which is called distributed generation. When we say DG, it is referred to a unit or to a quantity less than 10 megawatt. We call it distributed generation. For example, you place a photovoltaic cell on your rooftop, then that one we call it DG. You have a DG, since it is connected to the main system. Okay, so the photovoltaic cell in your rooftop, if you have it on your house, it can be called also DG. Dropout is a loss of equipment operation due to noise, sag, or interruption. Fault. When we say fault, that means we are talking about a short circuit. Fault transient, it is usually again a short circuit induced by lightning. So you could have lightning that hit the overhead line, or you could have let us say a snake that make a short circuit between two phases, and then of course the snake will be killed just in a short period of time, and then the power system will come back to normal operation. So it's because it say that which can be cleared by momentarily interrupting the current. Okay, so I have short circuit breaker open, it wait for let us say millisecond, then it close again. Fast tripping refer to commonly utility protective relay practice in which the circuit breaker or line recloser operate faster than the fuse. Okay, so we know that we have circuit breaker, we have fuse. Something goes wrong, we're supposed to have that the fuse will be blown out. But over here, what we call it fast tripping circuit breaker. So the circuit breaker will trip before the fuse. So that's why we call it fuse saving. And this is effective for clearing transient fault. Okay, because if the fuse operate, that means it need to be replaced. But over here, since the circuit breaker operate very fast, then it will be turned on again, because it assumes that there is something goes wrong for a short period of time. Let us say that we have a lightning that hit the overhead line, it goes a short circuit, then that lightning will go out, right, in millisecond. Then the circuit breaker can operate again without any problem. However, of course, if you keep opening and closing, even it is a millisecond, big consumers such as big industry, those who are making some product, of course their product will be affected. So we have what we call reclosing. The common utility practice used on the overhead line of closing circuit breaker within a short time after clearing the fault. So again, let us say that we have lightning that hit the overhead line, circuit breaker open, it wait for a number of milliseconds, then it close again. So we call it reclosing. Since it is assumed that the fault will be transient, will be stay only for millisecond or even less than that. Instantaneous reclosing, a term commonly applied to reclosing of a utility circuit breaker as quickly as possible after interrupting the fault. And the typical time will be 18 to 30 cycles. So don't forget that when we talk about cycle in Oman, we have 50 Hertz, so one cycle is 20 milliseconds. So if it is 30 cycle time 20, we are talking about 600 milliseconds. Of course, you know what we mean by ground. and we know also what we mean by ground electrode. Okay, what we mean by the recovery time. Recovery time, it is the time interval needed for the output voltage or current to return to the value within the regulation specification after a step load or line change. Okay, so it is the time interval needed by the voltage to return to the initial value. Also, it may indicate that the time interval required to bring a system back to its operating condition after interruption, okay, or dropout. This is for the recovery time, but for the recovery voltage, they define it as the voltage that occurs across the terminal of a pole of a circuit interrupting device upon interruption of the current. And you know what we mean by rectifier. It is a pole electronics that convert the alternating current to DC current. Well, when we say shielding, we talked in electrical technology about overhead transmission line shielding. So what we have overhead transmission line, right, that carry the different phases, so phase A, phase B, and phase C, that will be carried out. So we know that on the top of the overhead line, in the top of the tower, we have another wire, okay, that is running on the top, and we said that the purpose of this wire is to shield the structure. So in case if there is lightning, those lightning will not hit those overhead line, it will not hit the tower, it will hit this shielding wire, and of course the shielding wire is connected to the ground. Then that shielding will protect the insulator, it will protect the tower, it will protect the different phases. So the shielding, it is the use of conducting barrier between potentially disturbing noise source and sensitive circuit. So this is for the shielding overhead line, but also we are using shielding to protect those electronic circuit as well. Okay, and those shielding can be made from metal barrier enclosure or wrapping around source circuit and receiving circuit. So over here, if we have let us say if we have over here sensitive electronic equipment, and we know that this electronic equipment will be subjected to, let us say, to noise from somewhere, then what we can do, we can put it in a metallic barrier. So those shield, though the function of this shielding, it will take out the noise, so the noise will not go inside the device. Yes, this is which I have already explained to you, that we are using shielding wire to protect the power system. Okay, we have voltage again. We have voltage impedance or impedance, as you can see it over here in this diagram. Again, this is the measured voltage impedance and distribution system in Oman in one location. So you can see how the impedance look like. Whereas when we say voltage interruption, we don't have, the voltage will become 0 or less than 0.1. Okay. So this is what we mean by voltage interruption. CBEMA curve, actually it will be those curve. So this is the CBEM curve. So they will give you a relationship between the time is in cycle. So over here we have 1 cycle, 10 and so on. And over here we have the percentage voltage. This is the normal voltage that's supposed to be given to the device. Okay, this is the normal voltage. But sometime the voltage, of course, can go above the limit or can go below the limit. So anything above the limit, we call it over voltage. Anything below the limit, we call it under voltage. So over here, this envelope was produced by Computer and Business Equipment Manufacturing Association. So they say that any voltage within those limits should be okay for the computers and for the IT device. Okay, so they give they give a relationship between a voltage and between the time. The time is given in cycle. So you can see that the computer is supposed not to be damaged if the voltage, let us say, drop below even 20%, but for very short duration. You see that? This is very short duration. Don't forget that 1 cycle is a 20 milliseconds. So this is even, it is less than one cycle. It's about 0.5 cycle and so on. Then the voltage, or then the computer can tolerate the drop on the voltage even at 87% from the rated voltage for long duration. And also it can tolerate, or it can handle a voltage which is more than the rated voltage by another 6%, also for a long time. Okay, so those CBEMA curve, they are a set of curves representing the withstand capability of computer in terms of magnitude and duration, and it was developed by Computer Business Equipment Manufacturing Association, and it became a standard for measuring the performance of those devices. So any point below the envelope are presumed to cause the load to drop out due to lack of energy. Anything beyond that envelope, whether above it or below it, it will cause problem. And then this organization, which is the CBEMA, replace again that curve, the previous curve given in the previous slide, by this kind of curve, and they call it ITI curve. Okay, voltage disturbance that lie in the area indicated as a safe should not cause malfunction of this IT device. So again, this is the area in which the IT device should work without any problem. But of course, anything above the envelope, the device will be affected. Anything below the envelope, the device will be affected. And again, it is the same thing. So over here, they give the percentage of the nominal voltage. So now the voltage can go even to 500% compared with the rated one. 500%. but of course it has to be in very short duration. Again, in millisecond. Look at the time now, become even 0.1 millisecond. So don't forget that one cycle in Oman is 20 millisecond. Okay, that's all. Thank you.